formations. And that's not expected to be, monthly. It may be on a yearly basis. We really need to look at the data before we can decide what we can announce, because we don't really know what's out there. But it's not just small and smaller planets, but it's also the orbital periods. The giant planets in short orbital periods, we'll find those rather quickly. We'll go to Deborah and others to get confirmations, and so we might see that in about a year after the science operations begin. But certainly when we're talking about small planets in the longer period orbits, we're really talking about 2 or 3 years before we can announce those. And I do think, however, that it will be sort of a yearly announcement to tell you what we have found year by year.
All right, now we're going to the phone lines with David Perlman from the San Francisco Chronicle. All right, we might have lost David. Any questions here in the audience? All right. In the meantime, we'll go to Mike Meekum on the phone bridge.
Hi, can you hear me?
Yes.
Can you hear me?
Yes, we can.
Hi. I'd like to see if we can't further define the distances, the span of distance that you'll be taking images from. You were talking about parsecs, but I think the public may have a better sense of light years because they know that that's sun distance. Could we put it in those terms of the range that you'll be taking your images from?
Certainly.
Mr. Brookie?
Yes, that's straightforward. It's about 3 light years per parsec. So when we're talking about these dwarf stars, we're talking about light years like 30 light years out. If we're talking about stars like the sun, we're talking about something like 1,000 light years away. If we're talking about stars even brighter than that, we're talking about several thousand light years away. I hope that puts it in perspective.
Thanks, William. We're going to go back to the phone bridge with David Perlman from the San Francisco Chronicle. I believe we have him now.
Thanks very much. I was obligingly keeping myself on mute. I apologize. I was trying to get straight from you folks something about the continuum between the hot Jupiters, the hot ice stars, planets rather, and the terrestrial planets. There are a whole bunch of terms that have been used, and I'd like to get them straight and then tell me how they relate to the Earth-like planets that you're really looking for.
Deborah?
Okay.
Probably.
So, David, this is Deborah, and yeah, I guess there's not a good consensus among astronomers about what to call planets. Maybe we're afraid to take it to the IAU because some of our exoplanets will be tossed out. But you're right, there's definitely a continuum in terms of the size and the mass of planets, going from things we know in our own solar system. And so therefore, since these planets we know well, right, we can say that planets are terrestrial-like planets, Earth-like planets, and then the next jump is a Neptune-mass planet, and then finally a Jupiter-like planet or a Saturn-like planet. And so those are the terms that we throw around. And of course, we may be talking about planets that, even though they have the same size or mass, they're completely different because they're located at a different spot in their respective solar systems. So then they become hot Jupiters. They orbit in just a few days, or warm Neptunes that orbit in 30 days, something like that. So there definitely is a continuum. I think the one thing we've learned from exoplanet science now over the last decade and a half is that what exists is an incredibly random, chaotic, wild range of planets, and we started out thinking small, just looking at our own solar system, and our eyes have been definitely opened by all of the wide range of discovery and diversity of planets that have been found.
Another aspect of that I might add is the density of these planets has been astounding. We're finding planets that float like a piece of foam on water. very, very low densities. We're finding some planets where the densities are heavier than that of lead. So it's just astounding, the range of planets we're finding. And not only the planets, but the orbits. Everybody expected the orbits were going to be nearly circular when we first started this game. But what we've found is that the orbits are often highly elliptical. And that's been a big surprise as well. In fact, we're finding Jupiter's massive planets, where we didn't expect them. Everybody expected them to be out at 5 astronomical units, a long ways beyond the Earth. We're finding well inside the orbit of Mercury. So there's been nothing but surprises as we've built the technology and made these discoveries. And I suspect we're also going to find many surprises from the Kepler results.
Thanks, William. We have one question here in the audience, but we'll get to that in just a moment. One more phone call from Jacob Berkowitz.
Yeah, hello, Jake Berkowitz here. I'm a freelancer up in Ottawa, Canada, and I wonder a question for Drs. Barucki and Fisher. I'm wondering how the results from the QA2of5 mission have shaped, if at all, your expectations for the number of Earths or what might be found with the Kepler mission.
I'd like to take a stab at that. The QA2of5 mission is an excellent mission. It has made some great discoveries. It's a complementary mission to the Kepler mission. I've worked with Annie Baglin, who's the PI for that mission, and she has helped us understand what we're going to face. And what she found is many of the stars are more variable than expected. And so it's going to be harder for us to find some of these planets. And that's one of the reasons they haven't found as many planets as they'd hoped for at this time. But they're confident that they will be able to measure this noise, correct for this noise, and find many more planets. So the two missions complement one another. One of their major goals is to understand the variability of the stars themselves, something called astroseismology. Our major goal, instead, is to find Earth-sized planets in and around the habitable zone. So they complement one another, and we certainly cooperate with each other.
And we have now a question here in the audience.
Hi, Sanjay Talwani with Government Video Magazine. A couple of questions about the imagery you're undertaking. A couple of questions, but they kind of tie into one. If you could talk about the frequency of the images that are going to be taking. In other words, you're trying to detect change or motion, as it were. So do you have to snap images, every minute, every hour, every day? If you give some sense of that. And also, you've got 95 megapixels. I understand you're not sending all of those back, but you're selecting relevant ones. And if you could just maybe explain how you're paring down that data. And then once you have that data, if you could repeat the distance from Earth we're sending it and the kind of power it takes to send it back. And then finally, once those come back to Earth, I think this is in the literature you gave us, but how and where it's received on Earth. So if you kind of go from the frequency of imagery down to how we get the signals to Earth.
I can address that. The camera, if you will, takes an image about every 6 seconds. And we co-add them. That is, we simply add up the number of photons that we get out of each image for a period of 30 minutes. And when we telemeter the data down to the Earth, what we effectively get for these 100,000 stars is a brightness measurement for each star every 30 minutes. Now, we have a huge focal plane. As I said, it's a square foot of silicon. And because we're in an interplanetary orbit, we want to limit the amount of data we have to bring down to the Earth. So what we've done for each of the target stars is we've defined the pixels that surround each of those target stars, and those are the pixels that we bring down to the Earth. So we don't image in a conventional sense. We're really trying to measure the brightness of the stars. And in fact, we don't want the image to be too sharply focused because that would cause the detector to saturate and it would spread the photons too far across the focal plane. We want to count every photon that arrives so we get an accurate brightness measurement. So as the spacecraft is collecting this data, once a month, we have to turn the vehicle off of the science field of view, point the high-gain antenna toward the Earth, and we spend about a day sending the data down to the ground.